Thank you. So I'd like to go back to this morning's questions that I was asking about CWL. And it's not directed to any one person, anybody who is working in the general area, so Philip or Brigitte or anybody else can answer this question. Because I was trying to talk to several people, and we're sort of confused about something very, very basic. I mean, to me, in quantum mechanics, if you just give me a propagator, it doesn't, by itself, is just a, Green's functions, and what do I do with it? I mean, how do I use it? So propagator is useful normally, because one has an initial Hilbert space, a final Hilbert space, and then the propagator gives me a mapping from the initial Hilbert space to the final Hilbert space. Now, Philip, I think, is more Puritan, and he doesn't want to, at least I got that impression yesterday, about didn't want to talk about the Hilbert spaces. But other collaborators seem to be completely happy with Hilbert spaces. So let me just take this modest point of view that let's accept, because of the problem of time, let's just accept that there are initial Hilbert space and final Hilbert space, and the propagator is giving us dynamics from the initial states to the final states. And this dynamics is non-trivial, and as was explained this morning by Brigitte, that one should not think in terms of Hamiltonian. So this is just a propagator, and that's it. But then still, I got a mapping from the initial Hilbert space to the final Hilbert space. Is it a linear mapping? Is it a unitary mapping? And I thought that the answer to this was linear was yes, and unitary was no, but maybe I'm wrong about this. I would like to clarify this. And then I think in private discussions, Philippe was trying to say that if it is not unitary, there's still no problem. And so I would like to understand these issues, to clarify.
So I think it might be useful, I hope it'll be useful, to first of all clarify that I think about this in one way. I think that Jordan thinks about it in a somewhat different way, and I think it might be helpful in responding to your question to clarify the differences between those. So I'm going to pass it over to Jordan so he can give his description of how he thinks about it in Hilbert space. But my point will be, and I'm sure he'll respond, is that if you want to write this in terms of a Hilbert space, you have to have a Hilbert space for each one of these paths. And in fact, as you then go to the limit n infinity of those paths, you have a very, very large Hilbert space. In fact, it becomes infinitely large. But then there's a further maneuver which occurs when you're calculating, say, a propagator, which is then you take the 1/nth root of that. At which point, my understanding of what we mean by Hilbert space has kind of gone out of the window. I don't think about it in terms of a Hilbert space. I think about it in terms of a theory in which you start off with the fundamental entities being these paths. You allow, via the equivalence principle, as was explained by Birgitta, interactions, gravitational, between those. And you calculate from that a time evolution. Probability is not introduced as it is in conventional quantum mechanics as an axiom, whereby you have a Born rule after a kind of ex cathedra collapse of the wave function induced by something called a measuring instrument, which is not described by the quantum mechanics. What you have is a theory in which everything is described by these paths, and probability has to be introduced by hand in order to describe the lack of information that you may have about the past or the future or both. Okay? So that's my point of view. I mean, I'm just sketching it. But I think that Jordan is probably better at describing the Hilbert space point of view.
Well, Jordan and Yan Bei.
Oh, Yan Bei?
Yeah.
Oh, okay, fine.
You also have the same one.
I think Philip actually summarized my point of view quite well. If you're going to have a huge replication of the number of paths in a standard path integral, and you're going to talk about them almost like they're different entities, at least mathematically for the purpose of doing computations, if you want to say cut through that path integral and look at an intermediate time, then yes, it looks like the conventional quantum mechanics with an n-fold replicated Hilbert space. And so interpretational questions aside, if you just want to do calculations, this really just looks like a theory with gravitation and some large number n copies of your matter Hilbert space. And you can think in terms of conventional quantum mechanics for intermediate steps and doing calculations, and it's all well and good and normal. It really is standard quantum gravity, maybe with G Newton rescaled. All of the differences, I guess, come when you do what Philip said, and you say, okay, now that I've computed this propagator on this n-fold replicated Hilbert space, what does it mean? What do I do with it? Now to recover, say, a single object or a single particle interpretation and the limits that you want that. So let's say when I turn off gravity, I better recover normal quantum mechanics. Now I have to do something which might look kind of weird, which is to say, take the nth root of this n-fold replicated propagator. You know, it might seem ad hoc, and that's why we are doing calculations to see if it actually is consistent, but these are the kind of rules that one has to invent when you're trying to make mathematical sense of this notion. Are there further questions on that?
Yes. I mean, I don't know. Maybe this can be done in private. I don't mind. I mean, if you're getting
well, it could get quite technical, that's for sure.
So, so I don't mind stopping, and we can just discuss on lunch. I mean, I don't have any problem with that. No, because I still don't understand basic. What is the theory is what I would like to understand. What are the elements and what is the theory? And for example, in ordinary path integrals, we do have infinitely many paths, but of course we don't have, but we still have a Hilbert space there. And if you want to associate Hilbert space with each path, I mean, there's a way of doing it. There's a one number infinite product that one can take of these Hilbert spaces, a well-defined formalism, so you could do that. But somehow it seems like there is a resistance about having even a Hilbert space operator, anything. And then suddenly one says, one has quantum gravity. And then one says there is a replica of these paths for particles and fields, but there's only one gravitational field. Well, I won't call that quantum gravity, because you should sum over all possible paths in the space of metrics as well, in the space of gravitational fields as well. And there'll be replicas, or there will be something like that. So what is the kind of consistent viewpoint is what I'm not understanding. I mean, you should not have a single gravitational field, right? I mean, or you should not have just gravitational interactions. I mean, there's gravitational radiation. So that is emitted. It has its own degrees of freedom. It is not encoded in the degrees of freedom of this matter, And so how is that gravitational radiation being treated in this whole thing? Are there paths for this gravitational radiation? I mean, what people normally would say gravitons or whatever it is. So this is the kind of thing that's not clear to me. I mean,
did you want to go at that first?
It's honestly an excellent question, and it really cuts to the core of this. Treating the in and out states of the metric is a complicated question, and I don't have a good answer to you. But we are doing a functional integral over metrics, and so in a sense, if we limit ourselves to in vacuums and out vacuums, and we assume that we can integrate out the gravitational field just to get interactions between the matter field, we think we understand what that computation means. But as soon as we talk about non-trivial boundary data for the gravitational field, things do become complicated, and I agree, it's just not obvious from what we've said.
This is a technical, my answer to what you asked would be very different from Jordan's. Anyway.
Thanks. It's a question for Brigitte. So actually a pair. First, if you could just, because you're actually calculating something, do you see energy conserved in your calculations, or like?
I mean, thinking of the harmonic oscillator calculation. Like the other one we haven't finished yet. Harmonic oscillator calculations. Well, I suppose not, because if we had energy conserved, then we would only have that phase factor at the end of this projecting onto the time-evolved self of the state. So there's this very, very tiny change. Would you agree, Jordan? Kai? I mean, the non-unitarity part, I think, derives.
The question of energy conservation, I think, is a little less obvious because we have measurements acting on the system. And so if
I'm just wondering,
Yeah.
in your calculation framework, if you just compute, energy of what you're calculating, do you see?
In the,
Pass the mic over.
Just as a, I mean, I would expect energy not to be conserved because this theory will localize a wave function, and so you'd have to see some increase in energy. But I'm just wondering if, as you've implemented it calculationally, and you just calculate energy.
As we've implemented it, the calculation with the extended body in the low energy limit, where you have basically the harmonic potential acting on the center of mass, then it does look like a regular path integral, as we all know from Feynman and Hibbs. And so the technical part that you're doing certainly does appear to have energy conserved. But it's a combination of all those things together, and that when you then project onto the time-evolved state, you get something that looks odd, non-unitarity. So I'm not sure. Probably underneath it means there's something that's not correct with energy conservation. But the technical parts, this is the propagation that's going through these multiple Hilbert spaces. All of that technically looks like it's energy conserving. Yeah, but it's the structure. So if it comes in and it's non-energy conserving, it's coming in from the structure of the interactions between the replicas, which is non-standard.
Right.
Yeah.
Can you pass the mic over if he's going to ask more?
Yeah.
Just one more question, if I may. So what do you see as the relationship between the CWL theory and maybe a simpler to calculate Schrodinger-Newton theory? And is there, what do I throw away when I do Schrodinger-Newton?
That's for Philip and Jordan. They've thought about that a lot.
I think I wrote this down in a 2015 paper about it. You get Schrodinger-Newton. Yeah, I know. But I'm answering his question. You get Schrodinger-Newton if you go to the LP squared approximation. That's the lowest order perturbation theory in the CWL theory, and then you make a mean field approximation. Then you get Schrodinger-Newton. No. It gives different answers.
To change the topic and ask Michael Wright if he's still there. Are you still there,
Michael, are you still there?
Yes, I'm still here. I'm still here, Bill.
Good, good.
Good to hear you.
So one of the things that I was wondering, and this sort of came up previously as well, for you, tell us about one of the things that you found especially interesting in this huge archive that you have. For example, one thing that I would be interested in looking at was Stephen Hawking's first public lecture at the Rutherford Labs on his results regarding Hawking radiation. I don't know if you recorded that or not. I don't think you did. I was there, no. But that kind of a thing. What for you sure. Really strikes you as one of the most interesting things?
Unfortunately, Stephen Hawking's talk at the Rutherford was not one of the things we recorded. We did record the seminar at DAMTP in which he first announced the Hawking radiation result, because I have a very, very graphic recollection of just before going in the room of Gary Gibbons coming up and saying to me, "Do you realize that Stephen's changed everything?" And of course it was actually Gary Gibbons' voice which relayed this first sketch of Hawking radiation. That was certainly memorable. The things which mean most to me personally, to be quite truthful, would probably not be in the physics section of the archive. Passionately interested as I've been for the best part of 50 years now in GR and cosmology and and in foundations of quantum theory, I just don't remotely have enough serious mathematical background or expertise to be more than a, than a bystander. I hopefully cheer intelligently from the touchline occasionally. The thing which has probably made the deepest impression on me has been some of the talks on foundations of mathematics, which we recorded, particularly the ones concerning the work of Alexander Grothendieck. Now, this is probably terra incognita to many of the people in this audience, so I won't go on about it, but there is an astonishing part of the archive which consists of 137 hours of recordings of a series of courses and of colloquia that Grothendieck gave in 1973, which had been thought to be completely lost, but which in 2007, 2008, we discovered the recordings existed in Buffalo, in New York, and we recovered them. And as a result of that, there has actually been 3 conferences in Paris at the IHES and at the École Normale Supérieure, specifically about the content of the recordings. Sorry, do I take it that I'm muted or that nobody could hear what was being said?
No, we can hear you.
Oh, okay. Right. So that was my sort of rather long-winded answer to Bill. The importance of those, I think, has already been attested by the fact that there have been 3 international conferences focused specifically on the contents of those recordings. But of course, there's very, very exciting material in the physics part of the archive as well. And I'm hoping that it can be built on, and that we'll have many, many workshops and rencontres and interviews based on that material.
Sorry, do we have any other questions about to address to Michael? Okay. The next person who wanted to ask a question was Marcus.
Thanks. That's a question to Anatol, actually. So if I understand correctly, so you looked at essentially the vacuum state with respect to different mode decompositions or different modes to then recover Unruh or Hawking radiation. So I'm wondering, could you, with that approach, also model something like a black hole evaporation by introducing mode functions that change in time, for example, like dynamical mode functions?
Black hole evaporation in this business, like if you treat from the perspective of this Unruh-Schwarzschild modes, of course, you are assuming that there is vacuum state for those modes. But if you want to get evaporation, you need to assume you're accelerating relative to those modes. So you need to be in the accelerated frame. Well, calculation, we have not done this part. We didn't do calculation for evaporation process. We just calculated, let's say, the effect itself. It shows the analogy between Unruh effect and Cherenkov effect and many more. As far as the standard evaporation, it's probably easier to do using the mode functions which are already themselves in the accelerated frame, like those which I showed in the last, which are mode functions in original Schwarzschild coordinates. So for those mode functions, you don't have vacuum. So the state of the field is filled with photons. And of course, photons propagate also to infinity and contribute to the radiation. So probably that's the most straightforward way to calculate the evaporation process.